So Paul, at last we have a method for reliably finding planets. All we have to do is monitor a star and its radial velocity to a few meters per second for a few weeks, months, or years, and we can pick out its reflex motion caused by its planets.
This is not the way anyone thought this would happen, but it turned out to be quite effective. And suddenly it became very trendy. These people who had hitherto been very obscure were suddenly showered with grant money and jobs and telescope time. They got to build their own spectrographs and get huge amounts of time on the world's biggest telescopes. And so the data rapidly got better.
Yeah, it really became a huge industry where there were multiple groups around the world, and they, of course, got a lot of time, and so they made a lot of discoveries.
So here we've got a plot, which we'll loop over, showing the discoveries against time. So what we're plotting here is the mass. And remember, they don't actually measure the mass, they measure mass sign inclination. On average, for things randomly distributed, the real mass is going to be about 14% above that. So to begin with, there were only a few things which were pretty high mass close in. But as time goes on, first of all, they start finding things down here with lower and lower masses. And that came because they got better and better at their techniques. They got better software, better at correcting all these different problems we've talked about. And also they got to build their own spectrographs, which were purpose-built for this purpose rather than just borrowing someone else's spectrograph, which gave them more precision. The second thing that's improving is they're starting to see things out here further from the sun. When you get further from the sun, you're talking about longer periods. These things might have periods of 5, 10, 15 years. So you're not going to see them in a one-week observing one. You have to actually observe over many months, years. So as time goes on, this is where we're at the moment, at the time of writing this talk. These are the hot Jupiters. These are the things very close in, and you see they range from maybe just a few, less than 1/100th the mass of Jupiter up to 20 times the mass of Jupiter. Much higher than that, there'd be a star. And you're also beginning to see more and more objects further and further out. It turns out these are relatively rare. The bulk of the things, now we've got 10, 15 years worth of data, are out here, maybe about an Earth orbit out, so there'll be a period of a year or thereabouts. And they're even beginning to see things with periods close to, and masses close to that of Jupiter.
Wow, so if we look at this diagram, we see that there are a lot of Jupiters where the Earth is. So our solar system isn't obviously the norm. I guess, though, we can't yet see our solar system because we simply haven't looked.
We're getting close to be able to see something like Jupiter, something with a sort of like a Jupiter mass and a Jupiter orbit. We're not yet in a position to be able to see things like the Earth or Venus, let alone Mercury or Mars, which are way down here. Right. So these are still not like our own solar system. We're still talking about the hot Jupiters down here, and these things still, as we'll see in a moment, tend to be in the highly eccentric orbits. So we've got the hot Jupiters and we've got the eccentric giants over there.
So Paul, we have all of these big Jupiter-like planets in quite close to the sun, so not at all like our own solar system.
And if you remember, that's a problem for our normal theories. Our theories say you should only be able to form these big things out beyond the snow line, beyond the asteroid belt or where Jupiter is. So it's a real problem that we're talking massive things that should form a long way out, very close in.
So let's not give up yet. Maybe we can form them out where they're supposed to be formed and move them in rather than trying to form these big planets close in the first place.
So this is for a long time the standard theory for how these hot Jupiters got there. And it has a benefit that it was actually predicted before the observations. It's always, you have more faith in the theory if it comes on before the observations. Theorists are very good at explaining things after the event. There's a theory of migration. This came as a solution to some problems in our own solar system. The idea is that when the planets are first forming, they're still embedded in this protoplanetary disk, which is a very massive disk, primarily of hydrogen and helium. And some smart theorists had calculated that there'll be a reaction between these things. There's not going to be much gas drag, but the planet will generate ripples in the gas, and the ripples will have a gravitational pull back on the planet, and this will cause planets to move. This was come about amazing explanation for where Uranus and Neptune come from in our own solar system. Basically, the time it should take them to form out where they are is so long they should never have formed. So a standard theory was that maybe they formed in close to where Saturn is now and then moved out. But the theories could get them to move either way. Here's some simulations. This is a simulation of a flyby of a protoplanetary disk, which is the red, with a planet forming. And what you can see, this is a fairly massive planet, and its gravity has actually carved out a gap in the disk. And you can see a very characteristic ripple pattern coming in through there. gas is falling in here and spiraling around the planet to actually form the planet. This might be how you actually form something like Jupiter. So as we'll zoom in on this in a second, and you see the whole complicated ripple pattern out here. And these ripples can either move it in or outwards. In this case, probably it would move it inwards, but depending on the exact density of the disk and its temperature and how many planets there are, you can get this thing to move in or out or even turn around. So it's in some sense a very convenient model. You can explain almost anything you like from it.
Sounds very complicated.
It is a very complicated model, and because we know so little about what these disks are like in the first place, it's very hard to say what it will do, but it's certainly possible for these things to move around in huge factors. And now we're going to zoom in on the center here, and we'll see a disk around the planet, and this might be the disk of gas like the disk that formed the whole solar system, and a much smaller one around a planet, which might have formed, for example, the Galilean satellites of Jupiter, or the big satellites. And so here's we know these ripples happen because you can see them in our own solar system in the rings of Saturn. You've got tiny little moons forming gaps in the rings, just like we see in there, and they form this rather complicated ripple pattern on the side. And so we know that when you do have a disk and you have a mass in it, it can indeed open up gaps and produce these ripples. So it's confirmed in that sense. And here's a simulation showing how one of the planets can actually be moved in. So here you've got the planet. It'll actually be spinning around at enormous time, but they've cancelled that out and left it in the same position. And what you can see is as time goes on, in this particular simulation, the planet's moving itself in. The ripples over here and there produce a net backward torque, slowing down its orbit and moving it in.
And these other ripples are also caused by the planet as well. So presumably a big planet like Jupiter would affect everything else in the system as well.
And of course, in reality, you might have several planets, each of which generating their own ripples, and the ripples start interfering with other ripples, and it becomes incredibly complicated.
Right.
So how can we form hot Jupiters? Well, one idea would be that we have the protoplanetary disk and the planets start migrating inwards. The gas giants form out where they're supposed to form and then fall steadily inwards. And you produce an endless stream of planets all falling inwards until at some point the protoplanetary disk goes away. This is thought to be about 10 million years after the solar system starts forming. At that point, it's like a game of musical chairs. Everyone suddenly freezes where they are at that moment.
Oh, because all the gas is gone and this rippling effect that's sapping energy from the system disappears. And so you literally get these objects coming in and whatever's left is left, as you say.
So here's another simulation of that. So here we've got a planet, a star embedded in a disk and a planet orbiting around. So as time goes on, it's setting up ripples, which are causing it to spiral in closer and closer, faster and faster. And then at some point, there we go, the disk goes away, just leaving it where it is. And if you get it just right, you might be able to leave it like this is a hot Jupiter. But the trouble of this is it needs a lot of fine-tuning. These disks are supposed to hang around for about 10 to the 7 years, so about 10 billion years, whereas the time to migrate something in is only about 10 to the 5 years. So it
sounds to me like you would probably lose almost all your planets you formed under this scenario.
That is indeed the case. You'd expect maybe only 1% of planets to survive, the one that happened to be in just the right place at the exact moment. But that's kind of okay, because we actually only know that about 1% of planets have hot Jupiters. The other 99%, they didn't see anything. If you remember the survey, we could only see things that had massive and closer in. And it turns out if you do the sums, we're seeing that about maybe 0.5% or 1% have the hot Jupiters. So it could be the case that maybe this happens everywhere. All these solar systems form planets, and in the vast majority, it's just destroyed or still a long way out. And in the 0.5% or 1%, it just is caught at the right position.
All right.
So it's very destructive. So that's one possibility. Another possibility is that for some reason there's a hole in the inside of the disk. So the things migrate in, but then they stop migrating when they come to the inside of the disk because there's no more ripples around them. And so you just build up something really, really rather big here.
Okay, so in this case you get the first planet comes in, it quits migrating.
Stops,
and then it sort of bumper cars with everything else just piling in on top of it as they come in. And so you get to build a great big object up. But you have to make a big hole, so you say magnetic field, that's convenient.
Yes, whenever astronomers don't know what's going on, we say magnetic fields, turbulence, and we wave our hands and look goofy. So yes, well, let's magically assume the magnetic field from the sun goes out and magically clears the whole of the disk. And magnetic fields can do anything you like, so maybe it'll work. We know that stars have magnetic fields. We know it'll interact with the disk, so it's not
completely crazy. Okay.
But it's fairly crazy. This would have the benefit that these things coming in could be quite small because they pile up at the inside, whereas in the previous model you'd have to have lots of big things coming in. But there's lots of mass in a solar system. Maybe there are. Maybe our solar system did form 100 Jupiters and 99 of them fell in and one got left behind.
Okay.
The problem with this is it's actually a bit too good a solution, this whole migration stuff. I mean, bear in mind that the migration timescale is much too short. It can explain these hot Jupiters, but what about our own solar system? We've got Jupiter out where Jupiter's supposed to be. I mean, why didn't it migrate in or out or somewhere like crazy? It should do so very quickly. In fact, it probably predicts that most solar systems shouldn't have any giant planets at all because they'd all have migrated in long before they've had a chance to stabilize anywhere.
Right, and we've seen that as we've found more and more objects, there are a lot of Jupiters, and not really close in. A lot of them are out by the Earth, and it looks like there may even be even more out sort of where Jupiter's supposed to be. So maybe our solar system isn't completely weird.
Yeah, so this may be too good an answer. It gets things closer in, but maybe it gets everything too close in.
So we still have a mystery on our hands.